Right, no pressure. Right, yes, so unlocking negative emissions. So what I was going to do is spend the first few slides just talking about some of the concepts and some of the terminology that we use. I think that would be quite useful to kind of unpack some of that. And then I'm going to look at BECCS at a global scale and talk about some of the challenges and some of the assumptions that have been made around the role of BECCS in the context of negative emissions, and then briefly introduce some of the research going forward and what we're doing to go forward. Right, so these are my first few slides that are different interpretations of the same slides that we've seen from many of the talks. So this is where we are now in terms of temperature. The Paris Agreement in 2015 shifted the goalpost a little bit down towards 1.5 degrees, so even more ambitious than 2 degrees. Where we are now is we're already pushing 1 degree. So you can see in terms of the scale of the challenge, in terms of limiting global average temperature rise to 1.5 degrees, is we really need to get on with this now. Okay, so talking about carbon budgets, this is another stylized version of some of the graphs we've seen. So, right, yeah, so the black line is your net CO2 emissions. And what that hides is we've got positive emissions here, all our anthropogenic emission sources, and then this pale pink line here is the total negative emissions. Where we get this crossover point, and we've got what we call global net negative emissions, is the point at which your total negative emissions is greater than your total positive emissions. So at this point, you've got a net removal of CO2 from the atmosphere. And this is what we're talking about in terms of global net negative emissions. So I'll explain in another way some of the details around what we mean around that. There's lots of different ways of delivering negative emissions. John's talked about direct air capture. There's other land-based approaches such as afforestation, which is basically tree planting and managing forests where there weren't previously forests. What I'm going to talk about is just BECCS on this occasion. Okay, so a BECCS supply chain is basically the same as a fossil fuel supply chain, only instead of fossil fuels, you use biomass at the start. So the idea here is that the biomass material takes on CO2 from the atmosphere via photosynthesis. That's absorbed and held into the plant matter. You then harvest, process, transport, take that biomass to an energy conversion facility, capture and store the CO2. That's the full chain for a BECCS system. So CO2 storage is the amount of CO2 you store. That sounds quite straightforward. Sometimes that's confused with negative emissions. If you hear the word CO2 storage, that is not negative emissions, because all along that supply chain, you've got losses. So you've got tractors using diesel, you've got energy conversion losses, you've got stuff that comes off when you're drying the biomass. So you need to look across the whole supply chain to look at whether or not that BECCS system is actually negative at a project level. You can then add that up to a national, regional, global level and have a total amount of negative emissions. So this is our dark pink area below the graph. To get into the hashed area here, keep doing that, sorry, our global net negative emissions only happens when our total negative emissions is greater than the positive emissions. And at that point, you've got a net removal of CO2 from the atmosphere. So where this works in the context of carbon budgets, looking at the whole system, so we've heard talk about the difficulty of abating other sectors such as aviation and agriculture. You've got not so many technical options as you have in other energy systems such as the power sector, and you've got some very large social and political challenges if you try and cut out the emissions completely. To get to net zero, we're always likely to have some residual emissions from these sectors. So one way that negative emissions and BECCS can be contribute is to offset those hard-to-abate sectors. Slightly more controversially, you might have noticed in that diagram, there's an overshoot. So we've got our carbon budget, which is the total cumulative amount of carbon dioxide that we can emit to the atmosphere that's consistent with a certain temperature rise. If we go over that budget, we either immediately or later in the system have to remove and account for that overshoot, if you like. The advantage of BECCS is it provides this secure storage of CO2 and produces part of the energy system as well while removing that overdraft. But, and there's quite a big but here, there are massive uncertainties around this. So there's lots of, particularly relating to the magnitude and the duration of the overshoot, we don't know if in the future we can scrub that CO2 out of the atmosphere. The Earth system interactions are very complex. There's a lot we don't know about it. So it's quite a controversial thing. It also introduces the concept of moral hazard. So the idea of a moral hazard is that one population takes on a risk, but the actual impacts of those risks will be incurred by another population, in this case, potentially future generations. If we take on, don't mitigate enough now, and we have too big an overshoot that we then can't either deliver BECCS at the scale that we're assuming, or the technology doesn't work, or whatever, you've then putting a bigger burden of climate change onto future generations. But it could also be argued that there's a concept of reverse moral hazard. We've seen how urgent we are. We've seen how far away we are from meeting those targets. So maybe that's the argument that we should be looking at negative emissions and BECCS, and that would be another type of moral hazard to be not exploring these things. And I'm not going to answer which of those I think, but, well, draw your own conclusions. Okay, so the really important thing that I can't stress enough in this talk, or any talk around negative emissions, is it's not an alternative to mitigation. Even with the most ambitious mitigation that we could get at this stage, is we will still need negative emissions, and the less mitigation you have, the more negative emissions you need. So the scale of the problem is already massive. By taking our foot off the gas in terms of, well, we need to take our foot off the gas, but in terms of our efforts towards mitigation, it really doesn't make sense at all. So looking at the scale of the problem, in terms of CO2, CCS, this is where we are now. This is the result of one of the integrated assessment models. So integrated assessment models are large global models that model energy systems linked to the Earth atmosphere systems and map out potential energy and emission scenarios that are consistent with different carbon budgets and temperature targets. So this is one from the image model looking at 1.5 degrees and what's consistent. So the blue block is fossil CCS, the orange is biomass energy CCS. So we can see here we're on about 40 million tonnes of just fossil CCS. By the 2030s, we're starting to see a little bit of BECCS and quite a lot of CCS. And then that ramps up incredibly quickly up to 2100, to the end of the century. To try and make the point again about the role of mitigation, if you look at where we are now, so this line here is our current global emissions. I've taken out the fossil CCS, so I'm just looking at the component that's negative emissions. You can see that as we start to bring down positive emissions, it's only when it reaches this point that you can see that it's going to shift below zero on a global level. And so that's to make the point that you know, it really does matter what else is happening in the energy system. Right, so that's the kind of basic concepts and ideas. So this is now drawing on some research that I've done with various colleagues across the Tyndall Centre, where we've tried to unpack some of the challenges and assumptions that are made around BECCS. So there's not a lot of information that was available about what was used in the models at the start of this project. This is results from the Avoid 2 project. And through a process of expert elicitation and looking at the literature and looking at what's assumed, we came out with a set of assumptions, key assumptions, that have a very high influence on models, but potentially a low pedigree. And so they're ones that we need to look up in much more detail of what is actually being assumed. And again, this is where the scale comes in a great deal of importance, because the smaller scale, then the more reasonable your assumptions are. As we go to very, very large scale levels of negative emissions, obviously your assumptions become slightly weaker. So I haven't got time, don't worry, I'm not going to go through every single one of these. I'm going to look at CO2 storage because I thought that might be the most interesting. I haven't got any pictures of rocks, but this is as geological as I can get. Okay, so we worked with colleagues within the image model, which is one of the main integrated assessment models that contribute to the IPCC scenarios. And we got them to do a series of emission scenarios looking at different percentage probabilities of reaching 2 degrees and 1.5 degrees by 2100. And we drew out what they're actually saying is assumed around BECCS and negative emissions for CO2 storage. And we did this for all of those assumptions, but this is just the storage data. So this coincides with some of the data that Martin presented. So our total global storage across the period to the end of the century from all CCS applications is between 600 and 1,300 gigatons CO2. That's cumulative. The model splits the world into about 26 regions. Just over half of the storage that's assumed is located within 5 key regions: America, China, India, Western Europe, and then Russia or Mexico, depending on which scenario you're looking at. The maximum rate of storage in terms of annual terms, the highest rate in any region is in the US in the 1.5 degree scenario, which is just over 5.5 gigatons, with a range of roughly 1.5 to 3 gigatons in the top regions across all those scenarios. So that's the sort of scale we're talking about. So what we did was we tried to then go to the literature and have a look at how reasonable these estimates are. So all of the regional storage estimates are within the potential that we found published in the key regions, with the exception of Russia, where there's only a limited assessment of the storage potential. And we use data from the Global Storage Portfolio publication. If people have got more recent data on this, then I'd be really interested to see that. We're just trying to benchmark what's assumed in the models with what's available elsewhere. In the USA and China, this accounts for only 10% of the estimated capacity. So that looks like there's not too much to worry about there in terms of storage potential. This is total storage as well. This isn't just negative emissions. This is fossil as well. But note that the regional estimates are, at best, based on effective potential. None of these are properly matched assessments, so some are better than others. But it's looking like it's not beyond the realms of feasibility, the amount of storage that's assumed. The other thing to note, because I haven't talked much about the rest of the BECCS systems at the moment, is our primary bioenergy production regions are not necessarily in the same locations as the CO2 storage. So there are issues around trade of biomass and emissions accounting in particular. Do you give the credit for the negative emissions to the country that's produced the biomass or to where the CO2 is stored? These are things that have to be worked out, and I'll come on to these sorts of issues later on. Okay, so just a word about my net negative emissions and how, because obviously that's critical. There's no point in doing BECCS. It's harder to do than fossil CCS, and it adds an extra element to the chain unless you're actually getting negative emissions. And how do we do that? Well, we have to look across the whole supply chain. And there's lots of stages to that supply chain, as I mentioned. So the best way to do that is to take a life cycle approach, to look at all the different losses along, say, and kind of look up. And if you do that, you can look at lots of different factors. You can look at lots of different functional units across those supply chains. But we don't yet have a standard methodology for doing that. So this comes on to the future work going forward. So in the UK, there's a large greenhouse gas removal programme funded by NERC. There's 4 large consortium projects and a handful of smaller projects. And one of those is the FAB GGR project, Feasibility of Afforestation and BECCS for Greenhouse Gas Removal, of which we're a part. And we're taking a supply chain approach to look at both a global, regional and local level at the potential for BECCS. So the idea is we're looking at real-world feasibility of these supply chains. So that's the other thing around BECCS, is it's not a single thing. There's lots of, the same as John talked about different routes to CO2 capture, there's lots of different feedstocks you can use, there's lots of different pathways that you can use for transporting things and transporting the CO2, lots of different processes. So we're not looking at a single thing. So we've taken a supply chain approach, all of the supply chains ending in the UK, but through different routes before that. And we're looking up and down. So we're looking along the supply chain. We're looking at what would happen on a global scale if we introduce those types of supply chains. What are the environmental effects and trade-offs? How do the different supply chains interact with each other and interact with other energy and agricultural systems? We're looking at, in the UK at the ecosystem services provision, economics and policy dimensions of those supply chains. And critically, we're also looking along those supply chains at particular bottlenecks in terms of the people and the policies and the governance measures and the regulation of those supply chains. What do the farmers who will be growing the biomass think about it? Those sorts of questions, and trying to bring that all together. So the supply chains that we're looking at, we've got 4 supply chains. 3 of them are BECCS. One of them is an afforestation. It's not really a supply chain scenario, if you like. And we've built these up in consultation with expert stakeholders of what they think are the most useful and interesting supply chains to look at. So there's large-scale electricity generation using forest residues from North America. There's an energy crop supply chain looking at medium-scale CHP. and we've got one using domestic short rotation coppicing using an IGCC, integrated gasification combined cycle process, with a variation looking at hydrogen. So we've taken a modular approach, so we can slot in these variants, we can slot in a different feedstock, or we can slot in a different energy conversion process, and then really kind of unpack what's going on at that supply chain level. Okay, so my final 3 slides now are trying to answer the questions that we were posed by the conveners looking at the main science questions for a start. And that really relates to scale. How can we scale up this technology that's not being used? There's not a single net negative plant that's in operation using BECCS at the moment. So it's looking at how we can scale up those, and there's lots of questions that unravel when you start to answer that question. Look at supply chains. I haven't talked very much about biomass, but obviously that's critical. We're looking at very large scale production of biomass. That has to be done sustainably. There's no point in doing this if you compromise other issues in the process. This thing about Earth system responses is very critical. We don't know how the climate will respond. Can we remove carbon dioxide later, and will it have the same effect? What happens to the kind of Earth-ocean interactions? That's not my field of expertise. Please don't ask me loads of questions about that, but that is a key science question in relation to this, and there are many others. But I'd also like to say that it's not just about the physical engineering and natural science questions. The social science questions are also incredibly interesting and tricky around BECCS, particularly looking at the ethical dimensions and the governance and policy. So in that sense, I think the main barriers to the development of this technology are primarily non-technical. Similar with CCS, we know how to do it, we know how to do BECCS in terms of the technology and engineering. We don't know how to do it in terms of bringing the people and the policies and the motivation and the incentives together. But critically, if we don't have a sufficiently ambitious climate policy, this isn't going to happen. You don't do this for any other reason other than the climate, really. So unless we're pushing towards having a proper climate mitigation policy, then this also isn't going to happen. We need the governance and regulatory frameworks in place to manage those supply chains. There's going to be geopolitical issues. We're looking at different expertise, different industries across a global scale. So that's another challenge. Getting that sustainable biomass, I've already mentioned that. But also the lack of CCS infrastructure at scale. Without CCS, you don't have BECCS. We need the transport and storage infrastructure, and there's major issues around delivering that, and we're not starting soon enough, potentially. So for the policy and regulation, critical, the Paris Agreement. We talk about that, we have that lovely picture. Yeah, we've got the Paris Agreement, but we haven't fixed it. We haven't agreed how to deliver that aspiration. We've agreed that aspiration, but we don't know how to do it. And we need that in order to get progress in this area. And the accounting is really challenging with negative emissions. Again, it's something that there's lots of people working on. We don't have the answers to that yet. And the global coordination and governance is something we haven't seen yet on the right scale. To get a proper global response to this is we do need to rethink how we pull all that together at a coordinated global level. But I would say also we need to start on the ground. We need to start with individual projects and get a proper demonstration programme. Not just look at the engineering, but look at those social, political, technical, ethical and governance issues as well as the technical challenges. And then we can start to scale up. And that's going to require financing. So, sorry, I've just blasted loads of challenges and barriers and questions in there, but I think that is the issue with BECCS. You start looking at it and it does unravel quite quickly into a lot of challenges, but I wouldn't say it's completely unsurmountable. Further reading, here's some papers, including our book. I've got some flyers if anyone wants the detail of the book. Find out everything you'd like to know about BECCS and negative emissions in the book. Thank you.
So that is the first book on BECCS probably in the world. So first edition signed by the author. Right, questions then. Who's got? Philip, you've got an early question. Has anybody else got a question? I'm going to try the audience first, of course.
Chris from the University of Glasgow. I was just wondering, on a feedstock level, has there been any consideration as climate change does happen to a certain extent, which is known, how the feedstock level will change? Because say this week in the news has been a lot about coffee production. Now, obviously, that's not relevant to this. But
well, it might be. Coffee residues.
Well, I think for everyone in the room probably, but in terms of for BECCS, is there any consideration of how that will evolve?
Yes.
At the very primary feedstock
Yes,
level?
yes, there's quite a lot of work going on about that. So in the FAB GGR project that I mentioned, so one of the team at Exeter is looking at global climate scenarios and looking at the effect on crop production levels as a result of that. But the coffee comment actually, so roughly in these models, roughly half of the feedstocks come from agricultural residues, and you can use coffee residues to generate electricity. I mean, it's not mainstream, but we've got a PhD looking into that as well, and you can attach CCS to that, so that could be that's one of the a possible BECCS supply chain. Perhaps a niche one, but...
Another question? Philip?
Can I ask mine?
Yep.
I thought the elephant in the room for BECCS was availability of land for large-scale production of feedstock, but are you implying that's not the case?
Well, it's a question of how much you want, again, and this is why it links to the mitigation.
I live in Scandinavia, which is one of the biggest production areas for biofuels in Europe.
Yeah.
And I just can't imagine it being much bigger.
So this is not my area, but I think it's roughly, I mean, in the top paper on there, we've got a breakdown of what the land use assumptions are and what that means on a country level. And in the key biomass producing regions as modelled, which isn't necessarily how it happened on the ground, I think there's no more than 5% increase in land use in any particular region. Roughly half of the feedstocks come from residues, so if you have a bigger impact on residues. There's also a constraint in the model that you don't use forest land or land that can be used for food production to convert to energy crops, because obviously there's issues around that. But that's in a model. You can stop it doing it in a model. It's potentially much harder to do that in the real world. So it is an issue. It is a key issue with BECCS, yeah.
Just wonder, would it be a need for extra fertilization then? Because fertilizers, isn't that also a global problem to get enough, or it's used too much, or is that also in these models? That if you need to grow things more or grow more biomass, then you also need fertilization because you will not use soil that are already well fertilized? Yeah,
and that's why it's important that the kind of sustainability dimension of the biomass production, that you've got to kind of look at it in the round. You can't just look at the biomass production and the CO2. You've got to look at the other environmental implications as well, absolutely. And that's why you need a life cycle approach. So I don't know if that answers the question, but...
John Brenner. I wonder if there's any scope for gasification of biomass and taking the carbon residues and sequestering them rather than carbon dioxide. Is that something that's been considered?
Is that biochar, is it?
Yeah, that'd be pyrolysis, is it? So you're not completely combusting.
That's
the
right,
word.
yes.
Yeah.
So that would be...
But the reduced carbon, that's now granules, it's powder. That's possibly much easier to stabilise.
So, well, there's a lot of research going on to that in Edinburgh, actually. Colleagues of Stuart's are looking into that. It's not something that we've been working on directly. You know far more about that than I do.
Yeah, so that falls into the general bracket of biochar. So if you put pyrolyzed organic material back in the soil, then it can last for tens, hundreds of years even. So it's restocking the soil systematically with carbon, because global soils have been totally depleted by intensive agriculture, and they've literally got capacities of several billions of tons of carbon. So it's a huge storage resource which can, in many cases, in depleted soils, improve crop yield and improve agriculture and improve horticulture, not least coffee growing and chocolate bean growing, in fact. And there are many tests which are ongoing and going on around the world, and that all works fine. It works. The question is making it financially worthwhile for people to do that on a farm scale, because it's much easier for them to just put that and compost it into the soil to emit methane. Bad idea. Okay. Anybody else? Yeah.
There's a question about fertilising the Southern Ocean. I think it was in the context, I'm going back 25 years now, that one way the planet removes CO2 from the atmosphere is making calcium carbonate. And so anybody thinking about how we could encourage the planet to do more of that?
So I mentioned that there are quite a lot of different ways of achieving carbon dioxide removal, and that's one of them. In terms of the models, which was the focus of this research, it's only BECCS and afforestation that's included in the integrated assessment models. There are programs, the Horizon 2020, you've got a call out at the moment to try and expand the representation of other negative emission approaches within the models. Obviously, in terms of starting doing things in the ocean, you have a much more kind of, your social response to that is slightly more challenging. The science, I'm not sure how well understood it is, but that also, again, you need to look at how you're changing the ocean atmosphere interactions. If you start changing the CO2 concentration, the uptake in the oceans changes as well, and that all needs to be looked at properly. I mean, it is being looked at, but it's still not sufficiently understood.
Another thing which is working at the moment in this country is rejuvenating peatlands, because we're growing a lot of coal, effectively, as peat. And so since the Second World War, we've spent a lot of time unblocking the drains and draining the peatlands, and now we're busy blocking them up to make the peat grow again. And that's an interim, quite successful strategy, but it'll only get you through for the next 30 years or so.
And the other issue with, I mean, so the advantage of geological storage is the timescales of the storage and how confident you can be. Whereas if you've got land-based storage, for example, a forest, you've got no guarantees that that forest is going to be there long enough, because as soon as it's burnt or a disease rips through it or something, then that's all released back into the atmosphere again.
Okay, I'm going to cut it off there.